All right, so this lab is gonna use the same equipment. You're gonna have an induction machine and a dynamometer. Just make sure that, and there's a couple of one rotor induction motors. There's not too many, but there's a couple, but if it says one rotor, make sure that we change it and we use a squirrel cage, because this is gonna work on a squirrel cage. So the setup, easy. Basically, the setup is the same as you had last week. That's not gonna change. Input voltage, the multimeter, so we're gonna measure current, voltage, real power, and reactive power. In addition, we're gonna also measure the speed of the machine. I don't think on this one, and torque. Yes, and torque. So we gotta take the same measurements. There's two parts to the test, and ultimately what we wanna do is we wanna build this model. That's the goal of the lab. So what we want to determine what is the R1, X1, RC, XM, X2, and R2. Let me start with that. RC is the core losses of the machine. That is, and some of you in my lecture this week, we talked about this. These are the hysteresis and the eddy current. On a transformer, it's on the core of the transformer, and then we talk about how we use lamination, right, on a transformer. On the machine itself is the rotor core we're talking about. So if we were to open the rotor, pull it out, the rotor is not one solid piece, it's slices of this like little disc. So in order to minimize your eddy currents, your hysteresis, the only way you can minimize it is by the material that we're going to use, right? So that's how this RC represents those losses. R1 is the resistance of the stator winding, right? So if you look at, there is a stator, the piece that doesn't move, and then there is the rotor, the piece that moves, so that represents the resistance of that winding. And then we have the XM, which is the magnetizing reactance of the machine, and then we have the rotor winding resistance and the reactance of it. So there's two steps. Step number one is what we call the no-load test. So what you do is you're gonna have the dynamometer where you're gonna make the loading on the dynamometer to 0. So basically you're letting the machine run freely, right? The difference between a synchronous machine and an induction machine is a synchronous machine, part of the redundancy, it runs at a synchronous speed, right? In this case, they run at 1800 RPMs. Induction machines, if you have the induction running at a synchronous speed, you're not gonna get anything out of it, basically. So the induction machines cannot run at a synchronous speed. And we'll talk about that in a little more details also not next week, because next week won't be here, but the week after when I come back and talk about the characteristics of the machine. But basically what you're doing, you're letting the machine run freely, right, with no load on it. And what that does, if you look at the circuit, let me explain this. And I think if you were in my class last semester, you probably remember this. On a machine, there is this constant value, it's a variable, but it's what we call the slip. Slip is really, if you think what a slip is really the difference between the synchronous speed and the actual speed of the rotor. So if you can think of the rotor, right, going at a certain speed, the magnetic field is going at a synchronous, and the magnetic field is always going to run at 377 radians per second, and you can think of the rotor, which is the actual speed, trying to catch up with it, but it never does. Okay, so the difference between those two things is what we call the slip of the machine. So an induction machine, basically its slip is equal to the synchronous speed, which is the speed of the field, minus the actual speed. The actual speed is the actual rotor moving, divided by the synchronous speed. So when we are on this condition, no load test, okay, the synchronous speed, the actual speed I'm sorry, at a synchronous speed, that is almost equal to zero, but not quite zero. The machine doesn't, so if you have no load, it's trying to catch up, but it has no load, so it's trying to catch up with the fuel and it's really, really close to it, but not quite. So what happened is that this value, which is the resistance of the rotor winding, is defined by R2 divided by the slip. So if the slip is close to zero, this is actually an infinite value. So the way you can think of it is, oh, that's an open circuit, okay? So what happens when you are under no load conditions, the current goes this way, and it never gets to the rotor because of that condition, and it just boom, goes here. So that way, if the current flows through this branch right here, then you have the ability to measure some of these values of the machine, the R1, the X1, and the XM, okay? So all that. So that the main purpose, once again, of the no-load test is to have the ability to measure these values. This one you're gonna measure using your voltmeter, okay? So you get that. All right. So that's, once again, that's at no load test, I'm sorry. No load test. So once you get this information, remember, we're gonna measure voltage, current, real reactive power, and apparent power. So we're gonna get some measurements out of this. I know it's hard for you guys to see over there, but because I wrote it all the way here. So no load test results, you're gonna get real power, and the current on that current that I showed you that is going through that loop, right? And the way once you have that information, you can use this equation, and they give it to you right there on the lab, which is X1 plus Xm is equal to the measurement of real power divided by the current squared. So that gives you some value in ohms. Is the combination of those two values. If you look at that model over there, there's an X1 and there's an Xm, so they're combined. R1, you already measure it, right? You went with the ohm meter, you took that measurement, but you can verify the value by taking the real power divided by the current squared. And then you come up with a number that is fairly close, right? Now, so that's the first part. That's the no load, okay? In transformer, we call that the short circuit, the open circuit test. That's what we call it if you're doing a transformer, right? The challenge with the machine, with the motor, is that different from a transformer is that the secondary moves, right? On a transformer, doesn't move. A secondary just secondary winding, right? So then that's what the reason we got to deal with the speed, the slip, right? Because it's a function of it. So then we do the lap rotor. The lap rotor is when you put all of the maximum load on the rotor. Lap rotor, and you've seen it, you experienced lap rotor. When you jam your if you have one at home, if you have a food disposal, what we call disposal, I forget what they call that. You know, when you grind all the trash on the sink, if it gets jammed and you hear that, that's a lap rotor condition. There is so much load on the motor and it's not moving, but it's still pulling energy, right? So that's what you want to do right now. You want to get those motors to that condition where the rotor is locked. Okay, so that's what we call it, lap rotor condition. And what that allows you to do is to then measure the R2s or the secondary or the rotor characteristics of the machine. So maximum load, that's what you're gonna do on this one. You're gonna increase some of these motors, by the way, not all of them, but some of them. You put maximum load and then you follow the steps on trying to get the machine to the maximum current that they're asking you there. And once it starts getting to the maximum current, the rotor will start turning. So some of these machines the load is not enough to keep them, stand still. If it moves just a little tiny bit, it's okay. But if it starts spinning, then we're gonna have to use a different machine. Okay. If I'm not mistaken, I think. Oh, I wrote it. I think it's 1.5 amps. Yeah. So basically, what you're gonna do is you're gonna start increasing voltage, trying to get the machine to move. You have full load on it, and once you get to about 1.5 amps, then you start taking all the measurements at a live rotor position. Once you get to that, not moving. Remember, you don't want the rotor to move. So then you measure voltage, current, real reactive power at armature. At actual speed equal to 0. Now, once you have that, we have this. We can use this formulas right here, where x1 plus x2 is what we call xs. We usually call it, but here on the lab you're gonna see he writes it br. So it's the combination of the x1 and the x2. Okay, that's the combination. Now, the formula and then is put the formula there. R1 plus R2 is equal to real power divided by the current, right? And in addition to that, it says X1 is equal to 0.5 times X2. He writes it, it's the same thing, but he wrote it this way, okay? And it says, oh, by the way, this is a type, I think this is type C, if I'm not mistaken. This little table I was gonna show you, this is the type of motors. This is defined by NEMA. Right? This is a standard. So if you have a type A, B, C, D, and one rotor, and that's the reason why I was telling you, let's not do one rotor. If there is a motor that says one rotor, it's not down because our results won't work, right? You just don't match the analysis that we're doing. What we're doing is a type, I think it's a type A. So if you know, basically what it says is, oh, this value, X1 and X2, okay? They're half. So say, for instance, if you have 10 ohms, I'm just going to take 10 ohms. I know this is 10 and I know this is 10 based on this formula right here because it's a type A machine, okay? So you just got to follow this. This is the one that I said that you measure. You can also use these formulas right here, and they're on the lab. Yeah, it's a type A, where X1 is equal to X2. That's basically what it is. The no load case, and he gives you these formulas too. He says, at no load, I want you to, now he's asking you for the efficiency. So you gotta go through that. Just use the measurements that you have. Pin is equal to 3 times, and the reason is 3 times because you're only measuring one phase. This is a 3-phase machine. All you do is you take that one phase that you measure, multiply by 3, so that you get the full power in of the machine, right? So that you plug in those values, you get this number right here. The power input is really 3 times the current that goes in squared times R1 plus the losses. There's rotational losses on the machine, right? How do I get the losses? Well, it's PE minus 3 times I squared times R1, and then you put the value there of what the P losses are of the machine, which should be very. Induction machines are not as efficient as a transformer. Transformers are very, very efficient. Induction machines are less, right? And one of the reasons is because you have a gap. And on the transformer, you have the core, and all of the flux is inside that core. Most of it, right? I mean, there's always some flux that leaks out, but most of the flux is inside the core. On the machine, you can think of the core like this. If you can think like a transformer, what I'm saying is if you have a transformer, you have a primary and secondary, you have a flux that goes back and forth, like feet, but it's all confined inside the core. A machine, you can think of something like this. There is a gap, and the rotor is right here. So to get to that, you're always going to have a gap there, and you want to keep that gap minimum because once the flux gets on the air, you can think of current getting into a very high resistance material, right? It's the same principle. the flux on the core is, the core has very low, I forgot the words. There is is the analogous of resistance. How come I cannot think of the term? But in an electromagnetic circuit, right? The no, I'll think of it in a minute. But you can think of resistance. So the core has a very low, I'm gonna say, resistance to the flow of flux. The air goes up, so that's why you wanna keep, and that, for the flux to go through air, through the rotor, through air, back to the core, that's part of the efficiency or inefficiencies of the machine. If you look at the rotor, the piece that moves and the piece that doesn't move, the gap is very tiny, like very, very tiny. You obviously you never want them to touch, right? Because then you damage the machine. So that's what, like I said, that's the reason why the efficiency of an induction machine in comparison to a transformer is not as good. Transformers are in the ranges of 99.9% efficient. These guys are not as efficient. And you found that out on the last slide, and I'll go over that. So that's what it says. Try to go through it. If you have any problems reading it, let me know. As I said, very similar to what we did last time. You just gotta do, there's two steps. There's the lab rotor condition, okay? And there's the no load condition. That's what you got. Okay? All right. So you can start wiring and I'll go.
No, this is an induction.